All right, so in this video, we are going to talk about the value of buffers, all right? So let's say we have a situation, we have a strong acid, so HCl. That acid dissociates 100% and it breaks. So if we have 0.1 molar of HCl, we don't actually have 0.1 molar of HCl. What we have is 0.1 molar of H plus and 0.1 molar of Cl minus. So if we were to find the pH, that would be equal to the negative log of the H plus, all right? So that's gonna be the negative log of 0.1 molar, all right? And if we go ahead and we do that math, that gives us a pH of 1. Now let's say that we have a situation here where we have 0.1 molar of CH3 of acetic acid, CH3, CH2, COOH, all right? And our acetic acid has a Ka of 1.8 times 10 to the negative 5, and it has a double-headed arrow, which means it's a weak acid, so which means we don't dissociate 100%. So if we had, instead of having that forward arrow where we go through and we produce all H plus and Cl minus, we have some H plus and we have some acid. So initially we start off with all acid, and we have no. And if you remember, what's our definition of acids and bases? We have our acid here, and this is our conjugate base, alrighty? Because in the reverse reaction, our conjugate base will accept that proton to make acetic acid. How do I know if something is an acid or a conjugate base? The acid will always have an extra proton on it, okay? All right, so that proton, that acid is always going to have an extra proton. All right, so it's always going to be a situation where your acid is neutral with an H, and then your conjugate base is AC minus, or you'll have a situation where your H AC with a plus, and then your conjugate would just be AC neutral, all right? So your acid is always going to have an extra H plus. When you add the H plus, hey Ryan, what's up?
Hey love, just calling to let you know that I'm passing away on my way towards you.
Okay, I'll see you soon. Love you.
Oh, you too.
Bye. Alrighty, we get a value of 0x is equal to 0.0013 molar. Okay, so what that tells us is at equilibrium, our ratio, so this is our HA, this is our A minus, and this is our H plus. This means at equilibrium, we have 0.0013 molar of H plus times 0.0013 molar of A minus over 0.1 minus 0.0013, or 0.0987 molar of our HAC. Okay, all right, so what happens with our weak acids? If you look at the difference, if we go, so our pH for this again is still equal to the negative log of the H plus, but whereas here, all of our acid, this is a really drastic change in pH, okay? All right, so if we take water and you add in 0.1 molar HCl, it's all going to dissociate, you get a pH of 1. But if you dissolve, so you have 0.1 molar acetic acid, you get negative log of 0.0013 molar. All right, and that gives us a pH of 2.89. All right, so 0.1 molar of that weak acid is giving us a pH of 2.89, whereas over here with our strong acid, 0.1 molar is giving us a pH of 1. Why is this the case? You may be wondering, Dr. GB, you already hammered this in. We know weak acids don't dissociate all the way. The reason why this happens is because weak acids can act as buffers. What do I mean by that? Okay, well, let's consider a scenario. All right, so let's say we have HCl. All right, we have our 0.1 molar HCl, and and that gives us a pH. We have a pH of 1. So let's say we add nitric acid, so HNO3 minus another strong acid, and we add it until we have a final concentration of 0.005 molar. All right? Okay. Alrighty, so if we go ahead and we take now our concentration negative log of, 0.1005 molar, because again, we add that in, we are adding 0.005 molar H plus. That actually takes us down. So looking at that, looking at 0.0, looking at that, that may look like, oh, that may not seem that big, but the pH of this, just by adding in, we take the log of 0.1005, that takes us down to 0.998 molar from 1. Okay, so that's not a whole lot. All right, so Dr. GB, you're defeating your own point. Let's go back a little bit further. So let's say we're going to add in 0.1 molar. So now we have negative log and that 0.1 molar of HNO3, it's going to split up entirely, and then that H is going to add to that H, and we get negative log of 0.1 molar plus 0.1 molar. That's going to give us negative log of 0.2. It's going to give us 0.699, all right? So that's going to push our pH down a little bit, because if we add acid to our strong acid, those acids are just going to add together to make a cumulative effect. But let's take a look at our weak acid, all right? So our weak acid here, we don't just have, so with a strong acid, an acid contains two components. This is our acid. And then what's on the opposite side of the arrow is the conjugate base, all right? So this is our acid, and this is our conjugate base, our Cl minus. This is our acid, or our HA, and this is our conjugate base, or A minus. However, strong acids are strong acids because the conjugate base can't actually act as a base, so the reversed reaction doesn't happen, which is why we have 100% dissociation. Weak acids, however, their conjugate bases actually do their job. And so for every acetic acid, HA over here, that gives up its proton, you're going to have a certain amount of this conjugate base re-scooping that H plus back up and then becoming the protonated version of the acid. All right, so what happens here is, because you have both the acid and the weak acid and the conjugate base, or you can have a weak base and a conjugate acid, because you have both the acid and the base form present, you are able to resist small changes in the amounts and the amounts of acid or base that are added into the equation. For instance, if you go ahead and you increase the H plus, all right, so let's say I add in some HCl. What's going to happen is this reaction is in equilibrium. So you are going to have the reaction shift back to the left and make more of the protonated version of the acid, all right? And that's going to cause a decrease in the pH, all right? But this is going to happen, or not a decrease in the pH, all reticles. We're increasing, we're going to shift to the left. We add acid, yes, that's going to cause a decrease in our pH. Similarly, if we were to go and we were to add OH minus, so let's say we were to add sodium hydroxide, and the effect of that is if we would have H plus OH minus goes to form water. So the effect would be we would be reducing the amount of H plus. Our reaction would shift to the right to replace that H plus that's been depleted by being neutralized by the OH minus. And the result of that is we are going to increase our conjugate base relative to our acid, and that is going to cause an increase in the pH. Okay, so this action where our weak acid or our weak base shifts its equilibrium to resist adding acid or base means that the changes that are felt, the buffer is essentially leveraging its properties as a weak acid or base to resist when acid or base are added, all with the goal of maintaining its equilibrium constant or its Ka. So this is what the Henderson-Hasselbalch equation is telling us, all right? So if we recall, the Henderson-Hasselbalch equation is the pH of a buffer is equal to the pKa. Remember where the pKa is the negative log of the Ka, right? So that's the component that's coming from the equilibrium constant or the acid dissociation constant. This is the part that's coming from our negative log of our H plus concentration. But the pH is equal to the pKa plus the log of the concentration of the A minus or the conjugate base or the deprotonated form over the HA, all right, or the acid or the protonated form of our buffer. All right, so our pH is equal to our pKa plus our log of A minus over HA. So what this tells us is our pKa is set for a particular acid or base. All right, so our pKa is never going to change. So when we have a buffer, we start off at our pKa, our pH will go up or down depending on the ratio of these two. So if we go and we add in HCl to our buffer, we increase our proton concentration. What that's going to do is we are going to shift to the left, all right? Again, that is going to increase our HA and decrease our A minus. So what this means is we're going to have the log of a smaller fraction, which means this component is going to be negative, and we are going to decrease our pH. Similarly, if we were to add OH minus, and that leads to a decrease in our H plus because of the neutralization reaction, what's going to happen here is our HA is going to decrease, our acid is going to decrease, our conjugate base is going to increase. That's going to lead to a bigger fraction, which will be a positive after we take the log, and that will lead to, again, an increase in our pH. But again, none of these changes are as drastic as if you just had a strong acid or strong base in there already, or if you had just plain old water. So let's take a look at our calculation. And so there's two different ways that we can prepare buffers in the lab. And admittedly, one of them, the first way is the way that I always prepared buffers until I taught biochem, or actually the way I taught it until I dealt with an enzyme that was sensitive to metal concentrations, and then I had to do it the Henderson-Hasselbalch way. And that is you take a buffer that's a weak acid or a weak base, and you add the opposite, so acid or base, until you get to the pH that you want to be at. But frequently, the way that's taught in school, and that's like technically the appropriate way to do this, is to use the Henderson-Hasselbalch equation. So what you do is you add the HA, so we've got our strong acid, or excuse me, not strong acid, it's late. We've got our weak acid, all right, and then we have our A minus, all right, But our A minus, so whenever you commercially prepare a chemical, you're never going to have it in a charged state. You always have to have that charge neutralized. So usually if it's A minus, we're usually going to have some type of charged metal that's going to be our conjugate base, all right? So your acid is generally going to be in the acid form. Your conjugate base is generally going to be a salt, okay? Again, how do we determine our acid versus our conjugate base? Our acid, or our HA, will always have an extra A, or excuse me, an extra H compared, an extra H, and it will be one less negative than A minus. So we have a minus here, minus plus 1 is 0, all right? Similarly, if we have H2, oh goodness, H2CO3 versus HCO3 minus. Again, we have one more H over here. We're minus 1 over here. We're 0 over here. Similarly, this proton, the second proton on carbonic acid, can also fall off, and we can get CO3 2 minus, okay? So this is our, so if this is our HA, this is the A minus for this reaction, but there's also a second reaction where this is our HA for the second deprotonation event, and this carbonate is the A minus for the HCO3 minus. And how do we know? Because this one has one more proton than this one and is 1 electron short compared to that one, or in charge. And this one here, we have a charge of -1, we have a charge of -2 over here, so we've gained an extra electron relatively, and then we have an extra proton here that we don't have here. All right. Okay, so that's a lot of going back and forth. And then the question becomes, okay, Dr. GB, we've got our Henderson-Hasselbalch equation. We've got our pH for a buffer. We know if we have a situation where we have some amount of a base and a conjugate acid, we have to do this. And if you may be like, man, Dr. GB, what's going on? Okay, whenever you were solving for X in a weak acid or a weak base, you were doing this calculation. We just didn't call it that, okay? This is A minus, this is X over the initial concentration minus X, and pH is the X over here. That's just the H plus, okay? So that's all that is. So what we're gonna do now is I'm just gonna do a really quick sample calculation. I'm gonna walk you through how to do a buffer calculation. So I'm pretty sure in the pre-class videos we solved for the ratio of the A minus to the HA. So I'm gonna show you a different type of calculation that actually comes from the textbook now, where we're gonna do a calculation for if I give you the ratios, what are they? Okay, alrighty. So this situation is we have a 25.00 milliliter buffer solution. So this is number 45 in chapter 17 in the book. All right, so 250 ml solution. That is 0.250 molar in acetic acid and is 0.250 molar in sodium acetate. Okay, so acetic acid. All right, so really quick, you may be wondering, how do I know which is which? Okay, so your clue is this ends in acid. So that's your giveaway that that's your HA. And this one has sodium. All right, so sodium is your giveaway that it's a salt. So the sodium is Na plus, so your acetate must be 1 minus. So this is going to be your conjugate base. And so acetate, that's CH3, CH2, COOH. And this is Na plus and then CH3, CH2, COO minus. Okay? Alrighty, so we have gotten that again. Acetic acid has a pKa of 1.8 times 10 to the negative 5. All right? No units. So if we're solving for our pH of this solution, our pKa, we're going to have the negative log 1.8 times 10 to the negative 5, okay, plus the log of our concentration of A minus over HA. So, according to per our problem, we have 0.250 molar A minus over, 0.250 molar HA, okay? So, if we go through and we do that, we get the negative log, so negative log of 1.8 e to the negative 5, okay? So that's 4.75 plus the log of 1, so that's 4.75 plus 0 equals 4.75. Okay, so this reveals a really interesting situation where we see how what the pKa is. The pKa is the point, is the pH at which our A minus and our HA are equal. Fun fact, all right? Okay, so let's do a different situation. So let's say that we are adding NaOH, all right, to a point. And so in fact, you don't necessarily have to do it just at molarity 2. You can also do it in moles. So we could do 0.25, okay, so times 0.25. So that would actually give us 0.0625 moles over 0.0625 moles as well. So let's say we add a situation where we are adding 0.05 moles of NaOH. What's going to happen to the pH if we add 0.05 moles of NaOH? Okay, all right, so our pH is going to be equal to, again, 4.75 plus the log. Okay, so we have so when we add in our NaOH, that's adding an OH minus, we are going to subtract it. We are going to subtract it from HA. So that's going to be minus 0.05 on the bottom, and we are going to add it to A minus. Why? Because this relationship here, all right, so HA goes to form H plus A minus. If we are decreasing our H plus, we're going to convert our HA into A minus to compensate for that loss of H plus. So we are going to have 0.0625 mole of A minus, or sodium acetate, plus 0.05 over 0.0625 moles of HA minus 0.05 moles. All right, so that's going to give us 4.75 plus the log of 0.0625 plus 0.05. 0.1125 over 0.0125. Okay, so that gives us 4.75 plus, okay, so that gives us plus the log of 9. Oops, hold on, okay. All right, so log of 9, all right, so that gives us 4.75 plus 0.95, and that gives us a pH of 5.7. Okay, alrighty, so our new pH is 5.7, all right? So when we see here, when we add sodium hydroxide, we are converting HA into A minus. So our HA goes down, our A minus goes up by the same amount, and that results in an increase in our pH. Now, if you're like, Dr. GB, what do you mean? How does that compare? So 5.7, that's still going up quite a bit, right? Well, let's see a hypothetical scenario. Let's see a hypothetical scenario where we have 0.05 moles of just HA, and this is a strong acid, so we have H plus. All right, so we have 0.0625. All right, 0.0625. What happens if we have H plus floating around and we add 0.05 mole with nothing to counteract it? So we have no A minus to counteract this. What is happening? 0.0625 plus 0.05 log look at that, the minus log is 0.1125 moles, and I guess we should do that over 0.25 liters. Okay, all right, so if we take the crystal to 0.1125 divided by 0.25, okay, minus log of our answer, if you go through and do that, that's a pH of 0.35, okay? So if we have a situation where we have the same amount of HA, and then we add in a bunch of things. So if we were to add in a bunch of acid, we get 0.35. If we were to have the opposite scenario where we were to take away, so if we added NaOH and we were to decrease, so we have 0.0625 minus 0.05 over, 0.250 liters to get our volume. 0.625 minus 0.05 divided by 0.25. Okay, that gives us 0.05 minus log of 0.05 gives us 1.3. All right, so we're still lower because we don't have any conjugate acid hanging around. But we can see here, when we go from adding or subtracting from that, we go from 0.35 to 1.3. All right. Okay, I realize I'm probably rambling a little bit because it's 8:30 and I'm tired, but I wanted to show you here the difference. If you just have like if you just have a strong acid hanging around, you add more acid to it, you're going to compile it. If you have a strong acid and you add OH minus to it, you're just going to subtract and you take the pH from what's left over. But when you have a buffer, you have either a weak acid or a weak base, you now have to contend with the balance between the acid and the conjugate base. And that causes, because you are shifting around and you always have to look at the ratio instead of just the H, any changes you get, any H plus you add, any OH minus you add is going to be mopped up and the overall effect will be smaller. Okay? Alrighty. So that's what I've got. I'm going to stop rambling. I'm not going to overstay my welcome. So I'm going to end this video. I'm happy to answer any further question about buffers. I hope this extra clarification helped.